piece. Does this look familiar to anybody? No name, blank on the inside. I don't know if that's like, oh, I thought maybe it was a gift. No, just kidding. Here you go. Ah, nice. Very good. All right. So today we are going to be working through what we call logic gates. It's basically the next step in the progression of, I'm going to say, transistors in computers. The thing with transistors is we can use them, and they were used in electrical systems. The Cessna 172, which this is kind of a wiring diagram mock-up board for, part of the part I'll introduce you under the purple ghost later today, has a transistor for the lighting dimmer. But where transistors ultimately ended up going was our computer systems. So that's basically what we're going to be talking about today. And I just want to kind of point that out so you don't like get down this one-track mind of what a transistor is or what they can be used for. It's almost like saying a battery. We're going to learn about batteries. It's like, whoa, man, you can use those for a lot of different things. So today we're going to be looking at kind of the computerized function. So part of why I say that is what was the big, there were kind of two big things we use transistors for. So we're going to call in the class just to see if you caught it. What were kind of the two ideas of what a transistor either is or does? Who could tell me back? Why would I use one? Yep, so smaller current to open up a path for a larger current. Yep. Perfect. That is probably the main thing we're using them for. Smaller current to a larger current. The other piece, and we can do that either on off, or we can do it based on amplitude as well. So we can use it for if I get a small input that slowly rises, the big input would slowly rise. So we can do that both ways. The second way is basically it's a switch that a person doesn't have to flip, right? So if we can get it set up, we can stack a bunch of these transistors so that if we say, okay, I've got, this could backfire, but if I've got 5 switches, A, B, C, D, E, F, does that make it 6? If I've got 5 different inputs or 5 different switches, and I might want to have 7 different outcomes based on how these switches are set up, we can use those transistors to say, well, if A is open, I want to get a signal that's going to generally lead me to 4. But if D is open, I want it to generally lead me to 1. But if E is open, generally, and we get all this where we say, hey, if this one, then that one. Now, if we wanted to draw that out, it'd get really complicated if we were doing it with relays, because you'd have to have like a whole bunch of relays stacked up saying, if this guy's open, we're going to do a coil and a relay, and it's going to open this one, it's going to go to that one. Even explaining it, I'm like, it'd get weird. But if we use transistors, we're going to wire them up, and it's not till a little bit later in the lesson today, and you're barely even going to see it. We're going to wire them up just in a way to say, okay, if A is open, we'll allow power to go through. Now, if B is also open, it can continue, but if B is not open, nope, it's going to go straight to number 1. So that's kind of the, I'm going to say simplified, and hopefully it makes sense later. So logic gates, and this is going to be kind of the last slide you get as well, so intro, but you don't have to memorize it. Logic gates, I called it, they're kind of the guardians of digital. They're what make digital work for us. Digital, when we say, is either yes or no. We like to say it's zeros and ones. So when we're dealing in digital, it's basically yes or no, it's zeros and ones, it's on or off. If I want to send information electrically, I can use 2 different methods. I can send it analog, or I can send it digital. digital is our zeros and ones, or you could say it's ons and off. Analog is gonna use more of a how strong is the signal. So this is case logic here, but Morse code, how many of you guys all kind of know what Morse code is, right? Not you have it memorized, but you have the idea. Morse code was essentially one of the first forms of digital, right? Because a dot was basically just a short on, where a dash was a long on, but basically it was on or off, and then you had a gap. So realistically they had three messages. They had on, off, well they had on, long on, or off. If we were gonna write that in digital, what we might write for A is we might write it as a on, and then our off, and then our on, because two ons in a row makes it longer, right? And then the gap would be off. If we wanted to write C, we'd probably have on, and then our off, and then our on, and then our off for the gap, and then our on, and then our off. You get the idea. So in Morse code, if you're picking up a signal, does it matter how loud the little thing is clicking? Does it matter if it's clickety, or click, click, clickety, click, click, click? No. If you're shining a light at somebody, does it matter how bright it is? No, it's either on or off. So that's what we do with a digital signal, where most of electronics, or I should say in analog back in the day, it wasn't that way. So I put up an airspeed indicator. Now this is not electric, that uses air pressure, right? So you didn't learn about them yet, but basically there's a ram air pressure, and depending on how high the pressure is pushing into the back of this thing, ooh, that'll be a fun class, I can't wait when we get to it. When it pushes into the bellows, the needle's gonna move, and it's all based on how high the pressure is going into it. Now if we go up to this guy, he's got an airspeed indicator over here with some numbers. Now ultimately, we're gonna have a sensor that senses what the air pressure is, that's gonna convert it to a digital signal. But that digital signal is just gonna be a bunch of zeros and a bunch of ones, and they're gonna be coming across in a 0111, 0011, 0111. And somewhere along the line, there's gonna be a computer processor that's gonna have to not only convert it to the signal, but then also take that signal back and say, okay, so that tiny little pixel, do I want that to be on or off? Do I want it to be white or black? What about the one next to it, right? So in aviation, once we switch over to digital, we're not using what we call analog, or the intensity of the signal anymore. We're using, is it on or is it off? So all that just to get you up to speed with the difference between analog and digital. And when you're thinking logic gates, basically we're using our digital, on or off. Here's the cockpit I like. We call this steam gauges. So if you're not familiar with the term, old pilots like me would look at this one and we would say, oh, I love that cockpit. It's got steam gauges in it. And basically, it's kind of a joke when we say steam gauges. It means most of these signals are analog. They're going to run off a pressure setting. They're going to run off of how intense is the electricity going to something. And we've got a bunch of needles. We like needles, see? We like hands on watches. We don't like digital. Now, all you new whippersnappers, you come over here and you got all these fancy LCD or whatever that computer screen's made out of, digital computer screens with buttons on the sides, and you go, oh, yeah, this is better. Okay, it's better for cross country, I'll give you that. But so this world lives in the digital world. This one, most of that stuff is living in our analog world. So since aviation is going to digital, the FAA wants you to have a basic understanding of what's going on in that computer screen, so that when something goes wrong, you don't grab a voltmeter and go, am I getting a large enough voltage signal to this thing? You go, well, that's not even getting a voltage signal. I mean, it is kind of, but not the airspeed coming to it. It's coming from a computer on a digital bus. We'll talk more about that later. Do you have a question or just stretching it?
I'm just stretching.
Push-ups in. All right, I briefly talked about transistors and how many are in stuff, and I couldn't remember. So if you have an iPhone 15, I think my wife just got a new one because I had to set it up with her last night. That was a hassle. 15 billion with a B transistors in her iPhone 15. I'm like, oh the word, that's a lot of transistors. So obviously they're not this size. They're not soldered in. They are printed on a sheet like that. And even when we say the word printed, we're going to use, I have it in my notes, lithography is the word. They're going to use lithography to print. So the company I brought up is ASML, to get bored, ASML over in the Netherlands. Pretty cool. They pretty much own the technology for making the machines that make those things. So you never want to go to war with them. So billions of these little transistors that basically function this way, but they're all connected in a way so that you can do logic with them and say, hey, yes or no. If I close this switch, do you want the next one to be open or closed? And that brings us up to our actual logic gate sheet, our logic gate board. So what this is instead of drawing every one of these with the actual transistors that make them up, which would be kind of complicated because almost every one of these would take a couple transistors wired in a certain arrangement to give us the outcome. The programming people have basically got to the point where they say, you know what, I'm not going to show you all the way the transistors are wired on your circuit board. I'm just going to tell you what the end result is. So our end result is we have basically these gates. We have a NOT gate, an AND gate, a not AND gate, an OR gate, a not OR gate, exclusive OR gate, an exclusive not OR gate. And it's like, well, that's a lot to remember. And I'll show you on the last slide. Unfortunately, some of them have 3 lines coming in or more. We're going to pretty much stick with the 2-line ones today. I'll briefly touch on the 3 lines, but you can add more inputs to each one of these as well. It just complicates the matter. So if we're going to go through them, basically what we have is we've got the name, we've got the picture that it shows, because in really early programming, it would look like a wiring diagram, and they're going to wire this guy up into a diagram, and you're going to get a lab later today that'll actually show it, and you'll have to kind of sort through it, kind of like a wiring diagram puzzle, and they'll give you an input, and they'll ask you what the output is. So it's got the name, they call that algebraic expression. I don't think that one you really even have to be familiar with. I didn't learn it. The symbol can be helpful. And then the truth table. Truth table means, well, what's going on behind the scenes here? So the best way to explain this is to start with what I call the base gates. It's pretty much, okay, what are we going to build these 2 things off? I want to make sure I get my slide right. All right, so on my base gates, I have an AND gate and I have an OR gate. The AND gate, the way I try to explain this, and hopefully they always give you the chart if they ever ask any questions. The AND gate is the most, it's the most gentle, loving shape up here. It's got a nice smooth nose. It's got a lot of surface area there. So the way the AND gate works, if I put a signal, and we'd call it a yes or no signal, or realistically, because we're kind of talking electrical, we'd say voltage. So if I put a voltage here, and if I put a voltage here, because and what it shows up here is, okay, what is B? If B is no voltage, I'll go back, I'll go right in order. If I have no voltage at B and no voltage at A, I'm going to have no voltage at X. If I have no voltage at B and voltage at A, well, I'm still going to have no voltage at X because it's a AND gate, and an AND gate says if I have a signal at both of them, it's an AND. If I have a signal at A and B, I'll give you an output. So if it's one or the other, no signal. But if I have both, so a signal at A and a signal at B, okay, then I'll give you a signal at X. So an AND gate says I need to see a signal at both of them. It's a AND. I want A and B, and then I'll give you an output. Does that make sense? Okay, well, I gotta get my jar out for this one for sure. We'll start with the easy ones just because I gotta clear out the names. David Alvarez. So let's say I come into my AND gate. I have a signal at A, but I don't have one at B. Do I have a signal at X? No signal at X. So I'm gonna say no signal. I should probably do zeros and ones just to hold with it. So if it's 0, 1, we'd say, okay, gonna be a 0 out there, yep. All right, so that's an AND gate. That one's pretty easy to understand. I need to have them at both of them. It's AND. Okay, the other, what I would call base gate, is the OR gate. An OR gate, it's very similar, but it's got a little bit more of a pointed nose, and it's got kind of a rocker shape on the back end. An OR gate says if I have a signal at either one of them, if I got a signal at A or B, I'll give you an output on the end. So I'm going to start from the bottom again. If I have a signal at A and B, well, I do have a signal at either or, right? So it says, yep, I'll give you a signal out here. It says if I only have a signal at A but not at B, I'll still give you a signal out here because it's an OR gate, either or. Yep, we'll run with that. But if I don't have a signal at A and I don't have a signal at B, nope, I'm not going to give you a signal at X. So that's an OR gate. It's you'd say it's an either or, and we're going to run with that. That one's simple enough. Okay, so just to keep with it, so it's like we're not picking on people. Brian Erdy, if I've got a 0 and a 0 at A and B, what do I get at X? 0. Okay, that might have been too easy, but you know, we're getting there. All right, so that's basically the two base gates. You'll notice pretty much all the shapes are made out of that, with the exception of this NOT gate. That triangle, well, the triangle doesn't really mean anything. They just had to put something on the line, is my understanding. What means something is that little circle right there. That little circle in a NOT gate says, NOT. When we were like junior high, that was kind of cool, right? You'd tell somebody something, you'd be like, I had ice cream today. NOT. And it reverses what you're saying. So whenever you tag that little circle after the gate, it says, hey, whatever you're going to do, just reverse it. Nah, it's like an inverse. So on the beginning of some of our gates, you'll see they'll throw the N up front, and drawing-wise, they throw the circle on the end. So this is a NOT AND gate. This is a NOT OR gate. So it just takes your normal function of the AND gate and the OR gate, and it reverses it out the back side. So a NOT AND gate, normally on AND, if we had a 1 and a 1, our output would be a 1, right? But this goes, okay, 1, NOT, we'll make it a 0 out the back side. So if I go to 1 and 1, oops, reverse to 0. If I had a 1 and a 0, over on our AND gate with a 1 and a 0, it would go, well, it's not both of them, so I'm going to give you a 0 out the back side. But on my NOT AND gate, 1 and a 0, I'm going to give you a 0 out the back side. NOT. So we're going to give you a 1 out the backside. We're going to reverse it. So that's the not, I would call it a prefix because it gets listed at the beginning, not and, not or, exclusive not or, but pictorially it's that little dot that's after it. Make sense so far? Okay, cool. So that's the not modifier. The exclusive modifier is the X. So X in the word. Otherwise, when you get the double line up at the front of it, that's the exclusive modifier. I want to make sure I say this right. The exclusive modifier does not like pairs. If there's a copy, the answer is no. It likes to be its own person. It's like the girl with pink hair. We don't have anybody with pink hair, do we? That's like, I want to, well, we used to say they want to be their own person with pink hair, but now it's a thing to have pink hair. So anyway, if you have the exclusive modifier, it's going to look at the input and basically say, hey, if I don't have exclusively a 1 or a 0, a yes or no, the answer is just no, because I don't like to have people that look like each other. That's what the exclusive modifier does. So let's take the exclusive OR gate. On the exclusive OR gate, you see it's got the double line up at the beginning. Normally, an OR gate would say, if I've got either or, where's my back to OR gate, I'm going to give you a signal anytime I have a 1 in any of them, right? It's like, hey, if I got one on either or, I'm going to give you a 1 out the backside. But our exclusive OR gate says, okay, if it's one or the other, I'll still give you a signal out the back end. But if you give me 2 1s on the front end, where I normally would have given you a 1 on the backside, I say, I don't like those pairs because I'm exclusive. We're only going to allow it if it's 1 signal. So that's what the exclusive does, is basically anytime a matching pair shows up, it says, no, we're not gonna give you something out the end. So on the OR gate, really the one it modifies is the double, right? Well, if I wanted to do, this is a trick question here. If I wanted to do an AND gate and make it exclusive here, could I do that? Not really, right? Because an AND gate says, and over here, an AND gate, sorry, that one. An AND gate says, I'll only give you a signal if it's a pair. But our exclusive modifier says, I'm never going to give you a signal if it's a pair. So that's why you don't see an exclusive AND gate. You only see the exclusive OR, and they'll flip you over and say the exclusive NOR. So you can put both prefixes on. We'll go to our exclusive NOR gate. For exclusive NOR, it says, okay, first we're exclusive. It is if I see either or, but exclusive, and then I'm going to reverse the answer. So, if I do a 1 and a 0, that still allows us through the exclusive gate, right? So we're like, okay, we could still potentially get a 1 out of the back end. It's an OR gate, so I do have either or. So normally I would say, I'm going to get a 1 out the end, I'm going to get a signal, and then I hit the not. And I go, I don't get a 1, I'm going to flip it, and that's going to make me back to 0. So a 1 and a 0 gives me 0. It's a non-signal. So in digital, we write 1 and 0s. You could say on and off. You could say voltage or no voltage. But that's how these work. So let's see here. I think we just hit all of the gates they have listed. If I'm not mistaken, there may or may not be one other one. But mostly from here, what they do is, if they're going to get complicated, they may throw a third leg on there. And if they throw a third leg, hopefully they're going to give you a truth chart. And remember, this is the truth chart for the not and gate. So, anytime somebody asks you to do logic with these gates, they better give you a chart to work through it. because, man, you'd have to be, well, you just have to have a really good memory to do it any other way. So I'm going to take a chart and work through it every time. All right, so I have a video for you, because I like videos. The guy in this one sounds really funny. I'm going to admit, I sorted through like 12 different videos trying to find a good video, and he sounds funny. Maybe it's like me. But as far as understanding what's going on here, this does a great job. So we'll watch the video, and then we'll keep going. It's not going to be a break yet. Too early.
Logic gates are the fundamental building blocks of digital circuits. Most electronic devices use some form of logic gate, like smartphones, gaming consoles, or computers, and many more. I wanted to teach my computer science students how logic gates work, but the textbook does not show how a simple logic gate can be made practically with simple electronic components. So I thought there should be some practical way of understanding logic gates. So I started my search on the internet, and I came across a few logic gate learning boards priced at such a high price. Look at this one here, $27. So that is when I decided to make my own logic gate learning board. How hard could it be, right? Just open EasyEra and make something. Easy.
2,000 years later.
After many failed attempts of wrong placement or putting components too close to each other, making it impossible to solder, I finally made this. Wait. I need to explain to you how a logic gate works before we can look at this. Let's look at the simple circuit together. Here we have two switches, A and B, and one LED. Now, if I close the first switch A, we see nothing happens. But when I close switch B, the LED comes on. This is simple logic here. We know this LED will only be on if both switch A and B is closed to allow the current to flow.
Alright, just testing you, making sure you listen to me. So which logic gate would that be? And very good. So you see where we're going with this, right? Very good. Alright.
Now we can represent a closed switch as true or 1 when the energy is allowed to flow, or an open switch as a 0 or false since no energy is flowing. Using this knowledge, we can create a truth table. Here are all the possible states our switch can be, and we can see the output is only 1 when both A and B is 1, as we saw in our circuit. This is the logic gate AND it is represented by the following symbol. Let's look at another logic gate together. Here again we have two switches, A and B. Now if I close switch A, we see the LED comes on. And if I close switch B, the LED stays on. Now, if I open switch A and I keep switch B closed, we see the LED stays on as well. Constructing a truth table, we get the following results. We see that the LED is only off when both A and B
So that one is which one? Or, yeah, you guys are good at this.
is 0. This is known as the logic gate OR, and we can represent it with the following symbol. I know these concepts are straightforward and we are just turning switches on and off with our hands. But how does this happen inside the computer? For that, we use the almighty transistor. There are many different kinds, but they all work on the same principle. Here we have the 2N222 transistor, a common NPN BJT used for general purpose low power amplifying or switching applications. When you provide the voltage to the base, it closes the circuit between the two other pins, collector and emitter. Let's look at the simulation together. In this simulation, we are turning an LED on and off using a transistor. To supply a voltage to the base, I need to close the switch, and this will allow current to flow from the collector to the emitter. Your computer can do this with billions of transistors. I made 6 different logic gates here, which you can check in the link down below if you want to go through the simulations yourself. I decided to make the NOT, AND, OR, XOR, NOR and NAND gates for my learning board. Using these simulated gates, it was as simple as recreating them in Easy Era. After I finished the board, I ordered it from a local company here, which parent company is JLPCB. It is an awesome company because they do send you 5 PCBs free if it is less than 10 by 10 millimeters. If you want the Gerber files to this board, you can download it from my GitHub page for a low price of 1 subscription to my channel. Now, back to the PCB. You will need a few cheap components, a few transistors, LEDs, resistors, buttons, voltage regulator, capacitor and a diode. To solder, it is very simple, and there are so many videos online. There are also many guides regarding to safety, but what I found the best is that small amounts of fumes won't kill you. But just in case, make sure you have good ventilation and goggles. All the components are labeled, but if you are unsure, there is an instructable which will show you the correct orientation of all the components. Here is the finished project, the $3 board that you can use to teach your students about the different types of logic gates. All the inputs are currently 0 on this board unless the button is pressed to allow current to flow to the gate of the transistor. Giving this board a quick test and comparing them to the truth table, we say everything is working as it should. Now that we have a nice looking board to practice our soldering and construct simple logic gates with transistors, you are probably wondering, where will I use logic gates in my daily life? It might come as a surprise to you, but you use logic gates every single day without knowing. Computer programs use logic constantly to check certain conditions in our program that will determine an output. In analog electronics, we can construct many OR gates connected to motion sensors to build a simple alarm system where if motion is triggered, it will send a high output or 1 to the alarm speaker driver. I hope you enjoyed this video. If you have any questions, just leave a comment below and I will get back to you.
Alright, actually a pretty entertaining guy. Putting his videos together, sets the bar pretty high for us. So he used at the very end the motion sensors. So a motion sensor would pick up I don't even know how they work, but a very light signal and the light coming into the sensor change, right, is what they're doing. So very tiny voltage signal, but it's got to send it somewhere. So they'll use a transistor to have the motion sensor is the base connected between the base, right, base and the emitter, and then that'll allow the big signal to go from the collector. So he said, okay, so if I have any input from any of these OR gates, right, I'll set an alarm off. So on an airplane, now you guys are still kind of new, but let's like brainstorm. Almost shut down. Where might you use, let's say, that same type of OR gate with transistors on an aircraft? Anybody got an idea? You guys got a lot to learn.
Fuel alarm or whatever?
Fuel alarm? What kind of alarm are we going to say? Like fuel leak?
Low fuel.
Low fuel, okay, yeah. So if either of my tanks gets low, it says, hey, let's send an alarm out. That's a good one, yeah. I was thinking landing gear. So when we've got like 3 different landing gears, if all 3 are down, we might want to turn a light on. Well, that would be a AND gate, right? So if we had an AND gate, now on back end I got 3 legs. AND gate, that's the nice friendly one, right? So an AND gate would say, if I've got all 3 of them on, and yes, I'll give you a signal out here. So I might, if I say, hey, I got a signal, I'm going to turn a light on for the pilot that says, your gear is safe. And I might also wire in a AND, would it be an AND gate? I might also wire in an AND gate with a NOT on the end of it to say, basically, if I don't have all 3 landing gears up, I'm going to give a signal. So let's say I've got, yep, that landing gear is, we'll say down. That landing gear's down, this landing gear's down. That one's not down. So because it's not all 3, Normally it would be a 0, but whoops, let's send it a 1 to turn the light on in the cockpit that says, hey, your landing gear is unsafe. So this might be connected to a landing gear safe light, landing gear unsafe light. So that's just kind of the idea behind, even if we were going to use, whether you call it transistors or go into circuit boards, but that's the kind of idea we're going down at, just a really thin level of why we would possibly have logic gates. I'm gonna have to look and see if I can buy one of those. He said $3, didn't he? I don't know how old that video is, but that'd be a fun little soldering project instead of a multimeter. I should at least get one for me. Alright, oh, it blanked off. Here's what we're gonna do. I took off all your answers. So, your homework is gonna be to go through, I'm gonna find it, logic function. I didn't even know they made these things this big. It was getting a little ridiculous. Your homework is gonna be to go through not just one logic gate. They do say, hey, complete it for each logic gate, but it's actually then gonna give you a diagram. I'll put it over here. Then gonna give you a diagram with several logic gates coming together, and so that one starts OR gate, right? So if I have a signal on one, or A or B, it'll say, yup, give me a signal here, and then it comes through and it says, okay, I've got a signal, maybe, because you've got to fill out each chart. If I had a signal here, this is just a NOT gate, so it's going to invert it and give me the other side, right? So it asks you on this piece of homework, what would I have at C and what would I have at Q? Is the focus off a little bit? That kind of helps. So whoever gets this piece of homework will have an answer done for free. So let's say we have a 1 and a 1. So I'll do the bottom one. 1 and 1. Would we have a 1 at C? Yes, we would on an OR gate, right? So we'd put a 1 in a C. Are we going to have a 1 at Q? No. No, because it reverses it. Now you have my lecture material. I think they have in your book this slide. No, that one. This slide as well, or you'd be able to find it online. So what I would do is I would have that table next to me while I'm filling these out, just to make sure I'm not confused. That's a funny looking AND gate, but you notice it's got a nice big soft area flat back. So that's what you're ultimately going to be getting to, and then I got to grade this thing. I got to go through all the ends and be like, are the zeros and the ones in the right place? What a hassle. But we're going to do it for you. So back to this one, just to make sure we're all on the same page. I'm going to call this closed book because, okay, you could open your book, but I want you guys to fill in the end of them, and we're going to run through, we're going to do it just a couple at a time, and then I'll assign which one you're at. So we're going to put you on the spot. Elijah, come on up and give me this one right here. Elijah. And then Gavin, you're going to come on up. Oh, you get an easy one. And you give me that one right there. So come on up, Elijah and Gavin. Grab a marker. Write what's on the board. One. And. Tell you what, I know how to do this easier than drawing names out. I'm going to start on this side of the room. So, see how we follow instructions. Anthony, you're this one here. So follow the front row across. 1, 2, 3, 4. So your front row are these you guys. That makes Lee right here. And Kubar. And then we'll go back to that side of the room. I'm going to do this side of the room first. You guys, other than the first two, you seem smart. So, I said that wrong. What I meant was you first two guys that did it well. So, Charlie would be here, and it'd be Leo, and as we come across, so figure out where you're at. While you're figuring out kind of where you're at, I'll see if it's lining up right. That would put, so I got 4, 8, my 12th person is gonna be 4, 8, right there. So figure out what it is, come on up, right up, and we'll see if you're right. Now, if you can, don't use like the 0 or the 1 in your book, just use the logic of what it should be. So let's get this thing filled in. I'm gonna go with 6, 12. Okay, so that makes Abednego this guy. And that would be, once we get to the end of the row, we'll keep going across the back. Okay, this side? Show me I wasn't wrong. So we're gonna go with Trevor is gonna end up being this guy. Yeah, you're the exclusive or third one. That'll make Sydney the exclusive nor 0-0. And that means that Josh is gonna be our last guy. Computer programming for me is like almost just barely sounds fun, and then you get about 10 minutes in and I go, or not, or not.
You mean Nor?
Nor, yeah. Exclusive. Exclusive and.
Wait.
Okay, so it's an OR gate,
Or
so if either or are there,
but it's also
and
not.
so would it start out being just, if it was just an OR gate, would you get a 1 or a 0? You guys? So it's not exclusive, so this one was the one he had. If you were gonna draw it in a wiring diagram, his went like this,
I think Tim took yours.
like that,
Yours supposed to be 0.
over to our light bulb. So if either one of them, so that's an OR gate, so if either one of these are closed, we'd get a light. So if they're both closed, would we get the light?
Yes.
Alright, so, starting off, both of them are closed, so we'd still get the light. But then, they throw a reverse it. So it would.
I thought I had it, and then I only bought it.
It's, yeah. Alright, let's see here, we've got Josh here, and Timothy Peak here. Sure. Okay, I'm a little nervous. You a little nervous? Okay, we'll see if this works out. During the lesson, during the lecture, I wrote on the board in the back, that's the, hey, if you're done with labs and looking for something else to do. And I've had Nick and some of the instructors tell me, don't make stuff optional. And I'm like, well, it's just if they're caught up. I don't want to bury everybody with it. But I would love it if somebody could find online how, or just look how you would draw it with a transistor. Because you can make these with a transistor, like a multiple, right? But the other thing is, what was kind of fun is when he had that wiring diagram, I'll give myself a battery, plus, minus. So, we'll leave it up. So in a wiring diagram look, that was an OR gate, right? I'll put my switches. If I close either of those switches, I'd get this is a light bulb. I'd get a light at the end. So that's an OR gate. It doesn't matter if I close one or the other one, I'm gonna get a light bulb at the end. So it's really easy to draw with an OR gate. What gets a little bit tricky is if you wanted to draw it as a NOR gate, and then you go, ooh, how do I reverse this thing? And it'd be actually kind of fun homework. So what we could do to reverse it would be to basically have our input come out and have it, I'll draw it like this for now. Have it go through the coil of a contactor, and then our contactor, if the coil is energized, we'll say would open. I don't know if I drew those contacts right.
I think so.
You guys get what happens? If I energize that coil, this contactor's gonna, here, I know what I'll do. There. Except I want it to be normally closed. I know how to draw it in the other diagram, but we haven't done them much. So, this would be an exclusive, not exclusive, this would be a NOR gate, right? So, this was my OR gate. If either one of them are closed, it's gonna turn the solenoid on my contactor. And my contactor, if this closes, is gonna say, reverse whatever you were doing, basically. I think that would work. Because let's see, if we close one, well, if neither of them are closed, we'll start here. If I got 0 and 0, my output would be 1, because the power could go through the bottom, right? So let's go with my NOR gate. 0 and 0, my output would be 1. All right, good job, whoever that was. Nice work. If I have one of them closed, my contactor is going to energize, which would actually open it and switch me to a 0. So either one, I get a 0. 0, 0, we like it. If both of them are closed, my contactor would get energized.
Yeah, you need them both.
Separation.
You need them, so,
Oh,
you got it?
so wait, so it doesn't backfeed, you mean?
Here.
I don't know what you're talking about.
You need
Oh,
grounded and.
light bulb and then grounded.
Yeah, light bulb.
That's what we forgot.
And then this also grounded.
So I don't actually technically need them separated, I just needed a light bulb. There. That's what we meant.
Will that work?
The light's a diode, so it forces it to go on.
Yeah, if the light is a diode, or you had a diode.
There. I don't think it backfeed, but thank you, you helped me. Sorry, I was missing a piece. Let's get back to that. So, is our light gonna be on or off? We'll go all the way back to the beginning. If both of those are open, our contactor would stay closed, so I would be able to get power through my contactor, through my light bulb, back to ground. So if they're both open, I would stay closed and the light would stay on. Now, if I close this switch, now my electricity could run through that switch, it'd run through the solenoid, that would make my solenoid suck that up and open. Now I don't have power to the light bulb anymore, so if either one of those closed, there we go, we'd get the 0. If we close both of them, I still have my solenoid, sucks it up, no light bulb. So there we go. We drew our not OR gate. Kind of complicated, but really fun. Now, you don't all have to do this because it might confuse some of you, especially if you're just getting to where you're like, I almost had electricity, okay, so now you're messing me up. But if you're up to speed, you're ahead, you're Corbin back there and you're bored, drawing out, like in a wiring diagram, what each of these are, it's kind of a nice little practice. It's not just for knowing what they are, but actually for understanding how a wiring diagram works. Okay, if you're Gavin, Corbin's like, no. So if you're Gavin, it's a fun little thing to do. So we just double checked our NOR gates. Let's double check everybody else. 1 and a 0, good. 0, 0, 0, 1, good. 1, 1, 1, 0, good. 0, 1, 1, 1, good. Already did that one. 0, 1, 1. We did it! Now, I don't know how many of you guys just looked in the book versus doing it, but good job. We were a success. That means everybody should basically get 100% on their homework, I hope. I should get one of those clear pieces of paper and print off the answer so I can just lay it over your homework. I just thought of that. Old guy stuff, so I don't have to read each one, right? got 3 of them. So pretty much if any of those signals, is a 1, I get a 1 out the backside. Now I could add the not to it to make it a not OR gate. I think I could even do this, make it an exclusive not OR gate, which would mean it doesn't like pairs. I believe, I'm not 100% sure on this, I believe with a 3-wire exclusive, you're still allowed to have 2 of 3, you just can't have all 3, but that's where it gets a little bit deep, and we'll leave that for the engineers. What? I don't know, yeah. Alright, what we're gonna do is we're gonna take a 15-minute break, be back at 10 after. I'm gonna explain some of your homework, I'm gonna pass out some of your homework, and you got 2 labs I gotta talk about, 3 labs I gotta talk about. So instead of just bury it right now, we're gonna do a 15-minute break while I play spike ball. And then we'll come back at 10 after and talk about your labs. Alright. Is it bright out yet? Do you have light? Yeah. Oh, it's a little wet out.
Can't roll around in the grass.
break. We got a whole game done. 6 minutes. That guy sells those on Amazon?
I don't know, I kinda want one.
I'm gonna see if we can, I doubt they're on Amazon, but we'll check. Guy had logic boards for sale. See the $27 one.
Logic gates are the fundamental a few transistors, LEDs, resistors, buttons, voltage regulator, capacitor and a diode. To solder, it is very simple and there are so many videos online. There are also many guides regarding to safety, but what I found the best is that small amounts of fumes won't kill you, but just in case, make sure you have good ventilation and goggles. All the components are labeled, but if you are unsure, there is an instructable which will show you the correct orientation of all the components. Here is the finished project, the $3 board that you can use to teach your students about the different types of logic gates. All the inputs are currently 0 on this board unless the button is pressed to allow current to flow to the gate of the transistor. Giving this board a quick test and comparing them to the truth table, we say everything is working as it should. Now that we have a nice looking board to practice our soldering and construct simple logic gates with transistors, you are probably wondering, where will I use logic gates in my daily life?
I thought he was gonna be Indian at first. I saw him and I'm like, no.
It might come as a surprise to you, but you use logic gates every single
Like, you said about like Indians or something. They seem to be very good at like the sciences, like electronics and all mathematics and physics and everything.
There's a lot of them, and they speak English.
Yeah.
So I think part of it is it just comes across all your internet searches.
Yeah.
Right?
Just by the sheer numbers.
Yeah, well, the Russian guys don't come across your YouTube search, but it's write it on the board. So put it so I can see it. We got totals of 40 ohms, 40 volts. It's okay. 2 parallel. Just throwing you for a loop. Doesn't really matter if it's battery or not, right? So 40 and 40. Resistance total 40
Let's say it's not my
ohms.
max.
Voltage total.
I'll just say it's not my max.
Volts. And then what they give us out? Resistance 10
But last time
and
it
120. All right, I'm pretty sure we can get it from that.
Relative.
So they want voltage across here, but basically, we're just gonna do all of them. So we know we got a 10 here. So this one's actually gonna be super easy. Where do we have 3, or where do we have 2 of our 3? We don't have it on any of the individuals, right? But what about our totals? So we've got 2 out of 3 here, right? I got voltage and resistance. So those 2 I can plug in. So voltage would go up top, resistance would go here. So amps. Yep, so 1, that's amp. Right? So amperage, I could have drawn it in an I, but 1 amp. Well, especially because they're asking this one, but does all of the amperage go through that? No? Why not? Where else can it go? Yeah, does all the amperage, is there, if I got a bunch of amps running down the wire, yeah, they all, right? So that means the amperage here is gonna be the same 1, right? So now we can do 1 times 10, so we got 10 volts. Normally I solved the whole thing, but that one fell apart. Does that make sense? Okay. Oh, hey, it's time. Come on back. Somebody shout through that back door, will you? Hey, Austin, can you just shout through the door and say, come on back. Thanks, Austin. I got bad news, Austin. My boy changed his hairstyle. He went to, I think it was back when I was a kid, where they kind of part it in the middle and it's a little bit like, you got a curl going each way. It looks okay, actually, from my era. I don't know if his friends will like it, but good thing I got your name down. All right, that's where I was at. Passing out stuff. Here is your logic homework. Take your time. On the one hand, you can cheat, and this is super simple. All you gotta do is like copy the PowerPoint, right? But you do have to get the answers on the last one, right? I would suggest not just copying the truth tables. I would look at the AND gate, the OR gate, say what does this mean, and then figure it out for yourself, and then double check the truth table to see if you did it right. But there's that one, so that's coming out. This is lab 9, calculate power. Basically, this is, I'm going to say as complicated as it gets, but not really, because it's not impedance. Impedance was as complicated as it gets, right? So this is calculate power. So it's the same math that you've been doing. It's just, it's got the power added to it. And remember, that is our watt guy. Our watt guy said power up here, which is watts, is volts, which is E, or EMF, times amps, which is I, amps, current, whatever one you want to put them in. So, what I would do, if I was you, is I would just solve everything. Well, that's what it's asking for, is solve everything. There's only a couple of these that using watts to solve it is really gonna actually simplify much, because if you can solve watts, pretty much you could solve the volts, amps, resistance formula. But every once in a while, you'll get a question that'll pop up, and I'll see if I can, oh, this is dangerous. I'll see if I can draw one on the board that would make sense for where you say, hey, why would I ever want to do watts? I'm going to switch it to a AC power source just for the fun of it. And we'll go over like that, and just for the fun of it, we'll put a resistor in there. So we'll say it's 100 volts, and I got 10 amps, and yeah, see, it's not even gonna be that tricky. We'll say 100 volts times 10 amps. I'm just gonna do some math to save myself some work. 100 divided by 10, that's gonna be 10 ohms total resistance. All right, and we're gonna say 25 watts. Pretty much you could solve, I'll give you one bonus one there. We can solve that. So here's what I'm gonna do. We'll draw it out of the jar, and when your name gets called, you've got to give me one step or one number. We'll put it that way. So here's one with watts that yeah, that should be solvable. It looks like there's not enough info, but realistically, if they give us watts, we have a pretty good idea. We don't know what the actual voltage or amperage is in this one, but it gives us at least a relationship, right? So Gavin came up with our A student for the day. Oh, not today. Well, either way, I need to give me one number that's not in here. Well, yeah, so I want to know, here, I'll do like this. I want to know how many ohms that resistor is. I'll say that's ultimately, now the way I do it, I'm going to fill everything in. But can we start adding numbers? So just give me one number anywhere in here. When I say one number, let's do this, right? There's our volt amp resistance, volt amp resistance, volt amp resistance, volt amp resistance. Now, if we wanted to get really complicated, and here's where it might show up. Maybe I shouldn't even say complicated. I'm going to draw it in purple. We're going to make it our power triangles, just because we're going through it. So over here on our power triangle, I know it's 100 volts, so it's volts times amps is 10 amps, is I'm going to have 1,000 watts, right? Oh, you know what? I might have made a decimal error. I think I made a decimal error. Let me add one more digit. I think I need it to be that. Okay, continuing on. All right, so I need you to fill in one box somewhere. Now you can't fill in this one because we already know that's 5 ohms. We don't know what's there. 250 would go there, right? All right, so fill in one of my triangles. This is not a bad way to do it if you're still working on electrical. Just throw all your triangles up and be like, all right, let's start filling them in. So I just need one. Are there any of them that you can help me out, that we have 2 of the 3, or that we can just fill one in because we know one of the others? This? Yeah, good job. Okay, so if my total amps is 10, this part of the circuit is a series, right? So any little ants that go running down, they all have to run through this guy. So we could put a 10 here. And now the system breaks up, so we'll call on the next person. We don't want you to do all the math. So he gave me a 10. Pearson, give me a number somewhere. Now, it could be any of our triangles that have 2 of the 3. You can just give me the third one. Hint, hint. 50 here, good job. So that's gonna be 50 volts, right? 50 volts. All right, cool. Elijah.
Could you put, in the purple wattage one with 50, could you put the one above it? Could you put 100, 120, 250?
Here?
On the 250, the purple one with the 250.
Here.
Could you put 100 there?
I actually don't know yet,
Okay.
right? Oh, wait.
Parallel?
Okay, so, I got you now. Your logic behind that is if I lost 50 volts, if I have a voltage of 50 here, and I have 100 total, well, I must have 50 here, that's what you're saying? Yeah, you can do that. I didn't even see it that way. I was gonna see something else. I like it. See, there's a bunch of different ways. So he's saying up here, we could do 50, and the reality is, our wattage one, that means 50 goes here too, right? So you did, I helped a little bit. We put 2 50s in. All right, cool. I like that. That's not what I was gonna do. Does everybody see what he did there? So if we have 50 volts dropped across our resistor here, these ones are in parallel. So if I'm coming from this point, I got 100 volts, I move my voltmeter to here, and I would still have 50 volts pressure left, which means I have 50 volts across both of those, right? So, all right, here we go, next one. Ziegelbauer, you've got a bunch of really low-hanging fruit you could deal with if you wanted.
Could we put 50 volts on the other side?
Oh, man, you could put 50 over here. Which one? This one?
No, top.
This one? We could do it down here too, right? Okay, 50-50. And at this point, everything just got really simple, right? We just got to start plugging numbers. David, give me a number.
Can you do total ohms for resistance?
Where? I got totals kind of
Oh,
here.
you already got the totals.
Here, I'll give you some R1, R2, R3. That way you can point
So
me
over
at.
there, it's 5 ohms for both of them. So I don't know. I gotta do the math for what each resistor would be. 10 ohms?
Oh, I see what you're saying. So if we wanted to do a total of this circuit, you're gonna give myself another one of these and another one of these. You guys just don't like the low-hanging fruit, do you? Okay, we just drew in, if we were to simplify this down into a series, or take the parallel and say what it is, so we're drawing it. And you're saying, what we wanna do up here is
Figure out what each resistor is.
what each resistor is.
So I know that it's 5 ohms in that area because you already have 5 ohms over here.
So I got 5 here, so this whole section is 5.
So I gotta do the math on what.
Because 10 is here. Yeah, there you go, you gave us a number. We'll make somebody else take your logic and keep running with it. My brain's swirling because now there's 3 different ways to solve this at least, and you're all like picking little pieces of each one, which it works. All we gotta do is keep working. Brian, I need one number.
R1 is 10.
R1 is, how do you know that?
Because
What's 10, by the way?
R1,
The resistance? All right, how do you know it's 10?
because it's in parallel with the other one.
It's in parallel with this one,
Yeah, and they're the same value.
and they're the same value?
Yeah.
So basically what you're saying is, I don't wanna do one number, I wanna solve your whole box? Okay, that's what he's going with. So if he wants to solve the whole box, where he gets there is, if this is 5 ohms, and the total is, I did it right up here, we decided 10 ohms, right? So if this is 5, that means that section must be 5 as well. So we could actually then, he's just giving us like a million numbers. He's doing 5 ohms and 5 ohms, because we know that this has to be 10. Is this a ohm?
Wouldn't it be?
Oh,
10
sorry,
10 ohms?
sorry, that doesn't work that way. This would be 10.
They used to be 10 ohms, right?
Well, the whole section is 5, but individually they'd be 10. That's what you're telling me. 10. See, that's why I only wanted one number, Brian. 10, 10, yeah. 10, 10, 5. That's what you said, right? Right, okay. So, he just did the whole 1 over RT equals 1 over R1 plus 1 over R2. And he knew that the RT here had to be 5. Because if this is 5 and our total's 10, so he ran that formula for us. You know what, Brian? I don't like your answer, and here's the only reason why. I'm not convinced yet. Oh, it's because you got a 10 here. I was gonna say, I'm not convinced that they're equal. We didn't have that 10? All right. That's why I tried. So, while we're backing that up, I'm gonna back that up. We do know that top one has to be 5. Brian, I'm gonna give you credit for the 5 up here. Theoretically, I could have like a 6 and a something else at this point, right? I think. But the voltages stay the same. Here's where let's just do one number here. You gave us a good one. It works. I think you're right the way I drew it. And here's what I was trying to push towards. If we know this is 250 watts, you guys aren't taking the super easy. Is hey, you got 2 or 3 right there. So let's just solve this one. 250 divided by 50 is what? Did I do my math wrong then? Okay, 5, so this is volts, so, and this would be amps, right? Volts? Well, because that's our power one, because this is watts. I think, maybe my math still works out. I think we're still good. So now that we have that one, now we do know I got 5 amps through here. 5 amps through here. That'd be 10 ohms. Ooh. Why, and we put this in too early with Brian's, right? I think. So did I put this one in too early too with Brian's? I think I wrote those in when I was trying to explain Brian's. Because here's where it gets interesting. If my math was right, this one we end up with, I should put the ohms and whatnot, right? 50 volts is, this was amps. And 10 ohms resistance. All right, so if I've got 5 amps here, oh, we're still good. So if I got 5 amps here, Brian, how many amps do I got here? 5, and then we gotta go 5 amps, 10 ohms, 50. Brian's right, rats. He's right. We could have, instead of doing all his math up there, which we could just take our watts formula here if it's given to us and populate our triangles, right? So just populating the triangles, I could come down to this triangle and it's my power one. So 50 volts and 5 amps, 250. So this one's 250 watts. This one we could populate, it's 50 volts times 10 amps. 500, and basically I think we just filled them all in. So a double check at the end would be 500 watts plus 250 watts plus 250 watts should be 1,000 watts. 1,000 watts. 1,000 watts. All right. We got a little bit off in the weeds trying to tell Brian we're not sure, and it turns out he was sure. He just did like 6 steps in his head all at once. And I wasn't as fast. So that's one way to use watts, is you just use the watt formula if they give it to you, and it can help simplify things, or complicate things, if you want to look at it that way, because the way I did it. Okay, questions on that, or how you can draw in? I would recommend 2 different colored pens or pencils, just so you don't get which triangle is which confused, but I always look at it and say, hey, what's the easiest triangle to fill in and solve there? So here comes this homework at you. Should say homework. In a perfect world, you don't have to do any of it at home. these are labs, not quizzes. Send those back that way, I think I shorted you guys. So if you need help, by all means, come up and talk to me, Dean. I don't know if you'll get any other instructors to help you. They don't like electrical. Okay, Lee, you got an extra coming across yet? You'll probably get one out of the back row. You really didn't get extra? I thought I had extra there. We're getting there. Since I would recommend putting your name on it right away. Wow. Do I have that many too extra? Does anybody else not have one? You don't have any. Wow, I
I
just
have
not.
an extra, dash 18.
Lee. All right. So you all should have, we just handed out, what ones did I hand out? 18 and 9. Were those the only two I gave you so far today? Okay, make sure you have 18 in front of you, 9 in front of you, with your name on it. The last one coming at you here is 17. All right. Some classes would give you all these on the first day. You. Everybody got number 9? Okay. I might have an extra 9 if it turns out you didn't get 9. So you should have all 3 of these. By the time they get done passing, I'll leave the numbers up. 18, 9, 17. 17, I gotta grab my copy of it now, is going to be one of the ones that's under the purple ghost. That's not purple. It's blue. 9. There's 17. All right. So I'm going to roll this back out into the shop. Well, I don't know where I'm going to put this. I might put it right there. This has 2 different circuit boards on it. This one's got switches and labeling and lights and stuff. That is not the one you're using, just so you don't get all confused. This one has resistors and light bulbs. I went through about 3 of these and they worked. Hopefully the rest of them work, because one of them did not work at all. But this will be what's on your lab, and basically what they'll have you do is they'll have you switch essentially this ground wire on the ones where they want you to do it on resistances. That ground wire, I think it ends up getting plugged in on the end of the resistances. If they want you to have the ground wire set up to the light bulbs, there's a couple ways to do it. You could use a jumper wire with these little stake-ons. You can actually just push them onto each other like that. That is not an aircraft approved method, but test boards, it works fine. I did a lot of that back in the heating and cooling days. They will connect fairly decent temporarily. Really, if you wanted to do it, you could also disconnect the front end. I don't even know if you'd have to disconnect the front end. You could just put one here and one here and get the ground to just come through the wire and back out. But so that's how those boards are set up. You notice it's got a fancy little plug there. It's so we don't have to have 30 batteries, which I don't know if this makes it easier than 30 batteries or more difficult than 30 batteries, because now we have like 30 power cords. So we should have either enough or close to enough of these. And the idea behind these is you can take them to your workstation and plug it in. That just plugs in, and they all should be the same voltage rating, 12 volt. There is a fuse on here. If you blow the fuse, I don't know how many Dean has. So the idea would be try not to blow the fuse. Just follow the instructions. These aren't necessarily made to be working on everything, but you'll use a voltmeter to check where your actual voltage is. So, if you're not comfortable or familiar with a voltmeter, I'm going to draw this on the board a minute. We'll draw the simple one first. Basically, we've got a couple terminals on this side and and these two are connected. So basically, we have our battery, if you will, coming out of the wall, and it goes up to one terminal. The negative goes up to the other one. Those are just jumpered. And then one of your wiring diagrams will go through 4 lights. And they'll say, bring that back around to common. Do we need a light bulb in there so we see what's going on? Okay, so that's a complete circuit, right? And they'll ask you to grab a voltmeter. If we turn our voltmeter on, assuming that our power station is working and it's 12 volts, if I take my voltmeter, each lead set on voltage, and I go from this terminal to this terminal, what voltage should I get? Steven, what voltage would I get if I put my voltmeter from this terminal to this terminal if it's hooked up that way? 12, yeah. Cool. What if I go from this terminal to this terminal? Timothy Peak?
0.
0, because I'm not dropping anywhere, it's just connected with a wire. What if I go from this terminal to that terminal? So worried about picking on people. Lee? Also, it's just a wire between them, right? What if I go, we're assuming all the light bulbs are the same voltage. So what if I go from this terminal to this terminal? Timothy Peterson. I'm going to call the name first next time. Or like this. 12, yeah, because my positive, full positive, this one just comes back. Full negative, there's no load between. 12, okay. And drum roll, who's going to get the hard question today? Maybe I should put it up there before so it doesn't seem like I'm picking on them. Isaac Finney. We're assuming the light bulbs are all the same.
All the same.
All the same. Yeah, 6, because if we use Faraday's, let's see, Fleming, no, Ohm, who's the guy that had a calculator? Kirchhoff, thank you. If we use Kirchhoff's law, we're going to drop equal voltage if they're all, well, we got to drop voltage. I told you they're equal, so out of 12 divided by 4 is 3, so 3 volts, 3 volts, 3 volts. 3 volts, right? So if I'm going from here to here, I've got a 3 volt drop and another 3, so 6. So that making sense to everybody so far? Cool. And then it might throw some questions in and say, oh, snap, the wire broke. Your wire broke now, and all of a sudden our numbers are going to be different, right? Because you got this. Oh, that's Finney. You got back in the cup, Finney. You didn't want to stay. Parker Miller. Now, if I go from here to here, I already erased my 3s. I changed my circuit. What am I going to get? I broke the wire here.
0.
0, yeah, because my positive voltage, it'll go through the light bulb and through the light bulb and through the light bulb and through the light bulb. And because we're not going to have any amp draw, right? There's no amp flow because it's an open circuit, so there's no amp flow. So the pressure can get through, but we're not going to drop any voltage because it's going to get through and then it's just sitting there. Basically, at this point, you'd say it's static. I guess is what you'd say. It's like static electricity on a DC system. But yeah, on an AC, you'd still get 0. So good job. And the last one, I think the last one. Ooh, Austin. If I go from here to here across my break, what do I get?
Would that be 0?
That one would be 12. because I've got my full negative coming to this point, and we just said we still have our full positive because we don't have any amp draw coming to that one. So our little amps, they're all pressurized up. They're like, I want to go somewhere, but I can't get across the gap. So they're all pressurized up, trying to get back. So that would be 12 because we have the break in the line. Does that make sense when I explain it that way? Okay. Anybody else not making sense on that, or a question with why it would be 12 there?
What about that one of those first ones you did where you went down there and then to that side? Like it was.
Here?
Yeah, and then where the left exits.
So
You said
this
that
one?
was 0.
So if I go from,
The difference between this.
so if I go from here to here, Micah, now what would I get? For instance, we just said from here to here, we'd get 12. Is there any pressure difference along that wire?
No.
No. So we're gonna get the same thing here, right? It's our negative side of our pressure all the way to our positive side. We don't have any amp flow, so the thing to remember with these is if there is no amp flow, because we have a broken circuit, our lights, basically they turn back into a wire, because there's, the way you'd phrase it is there's only resistance to flow. But if we have no flow, actually that's a great way to phrase it. Why didn't I think of that earlier in the year? It's resistance to flow, but if you have no flow, no resistance anymore. I should have taught that 3 weeks ago.
So I guess I'm getting confused because if you have the 2 X's up there in the corner, you complete the circuit, you get 12 volts.
Oh, I didn't complete the circuit. This is open.
Right, but if you have the.
It's not an amp meter, it's a voltmeter. Oh, I see where you're going. Next question, if I were to put an amp meter here, well, now my amp meter, because the wires complete the circuit, now we're back to a complete circuit. Because even if this is broken, my little amp guys, they can run through my amp meter and they can finish the course. So an amp meter allows the amps to go through. If it's a voltmeter though, a voltmeter is not considered connecting the circuit. It's just taking a measurement. So if this is broken and I put a voltmeter across, it's still broken. All the voltmeter does is look at pressure. Does that simplify that or make sense now? So when you put a voltmeter on, it does not change anything in the circuit, it just gives you a reading. If you put an amp meter on, now we have the wire going through your amp meter, and it essentially will close anything that's between you because it's through it.
So that is a voltmeter.
So a voltmeter,
And it's open in the wire. What would that read?
we're going to read 12 volts
Okay.
because my potential difference between my plus and my minus is 12. My minus is going to stay the same all the way up here. So this point is the exact same as this point. On the positive side, because I don't have amp flow right now, because I have a broken wire, we're not counting those as being any resistance because there's no amps going through them. So I'd say ants, the little dudes, the electrons, the pressure is still there. They still want to run across, but there's a gap, and they can't jump that gap. So if you wanted to do a resistance number of just that gap, my resistance would be, where's resistance? Over here. My resistance would be infinite, my amperage would be 0, and my voltage would be 12. Okay. Alright, so that is whatever lab I just gave you, and you do it on the boards. And that's why we're doing it. We're working through so we actually see it in real life. Alright, and then the last side, the back side, I'd say if you get done, or if you feel like you're scheduled well and you're going to get done, if you just need a break. These are wired up from Marv. He used to teach the avionics class, and he's got a wiring diagram for them. And I looked at it, I'm like, whoa, that's complicated. I I looked at airframe, and I think we just took this lab and tossed it in the trash can for this year, even though it's like amazing. But basically, we've got a transistor, and we've got a variable resistor in here, and then we've got lights like it'd be on an aircraft. So this is very similar to how some aircraft are wired. And it's a fun one to just grab and work it, and you can see how a transistor changes the voltage. This is not basic electricity anymore, it's medium electricity. So I would not mess with this unless you got a really good grasp on electricity, but it is available. I put it on the available board for you to look through if you're caught up with your other stuff, or if you just need a break and want an instructor to kind of show you what's going on. But I'm gonna leave those on there. I'm gonna put all but one, because I want to keep one. The wiring diagrams for that. Sure. I'm gonna put them right on top of here. So if you want a wiring diagram for that, they're right there. That way I don't lose them. That's not a lab, it's a bonus, but it's a really fun one. Yeah, all right, I think that's all I got for today. So you guys are released. You can take a break if you want it, but lab time.
Question.
Yes.
What is this?
What is that? So that is an OR gate.
That's an OR gate?
Yep, so
It's not
the,
pointed though.
is it a little different shape? The backside that's curved tells us it's an OR gate.
Okay.
It's a little less bullet shaped is what you're saying?
Yeah, it, actually, is it supposed to be like that?
Oh.
I think that's a, I assumed it was an OR gate because that's I thought it was, I didn't.
Let me double check my,
Game.
let me double check, maybe they drew it funny.
I'm gonna be really upset.
It shouldn't be and, because and have a flat
Yeah.
backside.
The end, it looks like
That's
a
what I
V.
assumed.
Alright, back to our gates. That slide. Oh, because it's kind of,
It's supposed to be pointed like that, but it's,
that wasn't very nice, was it?
no.
Okay,
And then realized it wasn't.
let me point that one out. Good catch, and I hope you guys don't shoot me. Shoot the guy that made the lab. I'm still responsible for it. The backside here is really important for the AND gates. The ANDs have a flat backside. The OR gates have this curved backside.
So that's an OR gate?
So that would, yeah, let me double check my answers to make sure. I'm gonna say they drew it a little funny.
These two are OR gates.
Alright, what one is that?
18. Yeah, it's, they're supposed to be more pointed. If you look up there, it's like, it has a point. But these are rounded.
Oh, I saw the background and it was,
Are they?
I was like,
I
I'm
haven't
running
done
wrong,
lab
bro. I
before.
did the whole lab,
Put me back a page, will you?
but I looked at all of them.
Okay. Oh, so that's just OR, so that's the only one with pictures. Okay. I gotta do my logic then and figure out what it is. So, let me work backwards. I got a 1, and a 1. 1 plus a 0. I believe that is an OR gate.
Okay.
Alright, I am terribly sorry, that is a bad drawing is what happened. So on the last page, where it's got the complicated ones, those are OR gates that have the very much curved side. The middle one that's got the flat with a big D, that is an AND gate. Question 3, question 1, what do you call that? Question 1 and 2, it's this one. Try not to give you the answers. Alright, this one here, what he was pointing out is it's very much curved, which tells us OR gate, but they didn't follow our, it's a bad drawing. The nose of it is kind of a funny shape. The nose of it looks like an AND gate, but the back side looks like an OR gate. So whoever drew this thing, didn't do us any favors. It is in fact the ore, cause you're looking at the curve on the backside. So make sure you're looking at the curve on the backside. So they're ore. I'm gonna have to double check online now and see where he got those drawings from.
Amps don't change in series, right?
Correct. Because they all have to take the road, right? Yeah,
I'm still a little confused. I get this. You close it with a voltmeter. You would read 12 volts because you're essentially taking the entire circuit then, right?
yeah, so if we simplify it, just down to a battery, plus minus, resistor, and a switch. If our switch is open, what would we read here?
Is this
So,
12 volts? Or
so 10 ohm, we'll say.
we would read 12 volts, but
We'd
there's
read
0
12
amps.
volts, but there's, and
Oh.
there's 0 amps.
Okay.
Yes, and but, whatever word you wanna use. So with this open,
With a voltmeter, obviously.
yep, so 12 volts with a voltmeter. So that's, if we cut that, basically I could've just said, put a switch, and switch is open.
Yeah.
So it does the same thing, we open the circuit, and I just realized that's a decent way to explain it. If there's no amp draw, basically mathematically, the resistance, it goes to 0.
Right.
Because,
Total resistance. Kind of, maybe
yeah,
it's a bad way to say it, but.
it's 0, because this one goes to infinite. This is an infinite resistance, and,
So if you were reading it with an ammeter though,
So
then
if-
you would get the flow. Because
yeah.
That's a question
so-
I got wrong.
Yeah, so if I put an amp meter on there, inside your amp meter, there's a wire that goes between, and then it senses the magnetic field. So putting an amp meter on there, the current doesn't flow through here, like it,
Right.
but it goes
flows from
through
there
the
to there.
amp, yeah.
So now, what I was getting confused on, earlier when you were doing these, before we did the break,
Yep,
this is a solid line right here. You said if you measured it from here to here, it would be 0 volts, right? Is that what you said?
yeah, so let's draw it in that way. Got a little messy up here, so clean it up. So, if I draw it in that way, that just means it's a portal, right?
Yep.
So this'll make it really jump out at you, right? So if I measure at 12 volts here,
Because you're on either side of the.
yep, on either side, well, I'm connected to ground, so I'm gonna leave my voltmeter there. If I put the other one here, well, it's the same exact, I'm connected to ground. So whether I draw it as grounded or I draw it as a wire connected, the wire is not any resistance. So we're not gonna lose any voltage across the wire.
It would be 12 volts.
So we would,
Like if you.
yeah, correct, yep.
Now what about if you take the voltmeter here and there? Because
Isn't that what we just did?
there's no resistance. Oh, sorry, I thought you meant there.
Okay, so here to here would be 0. Because it's, I'm sorry, I think we just said two opposite things. So I'd be 0 here because it's the same wire. From here it would be 12, because this point is my plus 12, right? We could say plus 12. This is still my, I'm gonna call it 0.
Yeah.
If I go all the way to plus 12 here, I gotta make that one 0.
So what I'm getting hung up on, I think that makes sense. Measure there to there, it's 0 volts, because there's no, it's a wire.
Yep.
So simply putting,
Let's say there's only one amp going through here,
so if you put a gate in there, or an open switch in there,
and it's the same
Yeah.
amp that goes through this.
and you measure from here to here,
So now that,
that's still 0 volts? I guess it would be, because there's nothing in between.
yeah, so let's see here. So here is down on my battery, this is the negative. And it might be easier to think of it as -6, +6. It's a difference between those is 12, right? So if we had negative and positive, so my -6 still gets up to this point. So you could theoretically say, I got -6 there. My +6 wouldn't be up here yet. So I still have a 12 volt difference across that point. Is that what we asked?
No, sorry.
I might have.
I thought the one time we were looking at it, you put the voltmeter here, but
Don't ask me, I
and
don't.
there.
Okay.
What would that would be 0 volts as well.
So this one's still -6, right? On the -6 side. This one's my +6 side. So I would -6, +6, that's plus. That's plus. It's a 12 volt difference.
So then, if you close it and still keep it there and there, does that automatically go to 0 volts then? Because it's just a wire?
Yep, I close it, it goes to 0. So these would all go from, when it's open, they're all gonna be 0 volts across, right? No voltage, because there's no amperage.
Okay.
As soon as I close that thing, now I have current. Now that I have current, the resistance is resisting, so I'll end up with 3 volts, 3 volts, 3 volts, 3 volts, if I were to go across each one.
Wait a minute. I had that right.
Alright.
That's what
I'm still struggling for some reason, but
had
that's alright.
that
Maybe I
right.
just need to walk away a little bit. Parker has a question.
So that means that.
I guess I'm just getting confused because it feels like if you have an open switch and use your voltmeter, you get 12. But then when you close it and you measure it, you get 0.
Oh, yeah,
Yep.
that's
Correct,
where I
and the
went
reason
wrong.
is, it's back to, if I have no amp drop, I'm not gonna have a voltage drop across these light bulbs.
Okay. So you still have the pressure. You still have the voltage
Yeah,
in the system.
the pressure's still there, but I'm not
You don't-
losing any. And that's why we use that word voltage drop. I don't
Okay.
drop any voltage.
Yep.
Because if we put our little triangle under there, if my amperage is 0,
0.
I'm gonna have 0 up here.
Yeah.
So
Okay.
as soon
So
as
it's
I
the
change, as soon as I
resistance in
change
it.
my amperage to, I don't remember what our amperage was, 3, now I will have some sort of voltage
Yeah, you
drop
can
up
figure
here.
that out.
Okay. And this is all because using a voltmeter doesn't induce current flow.
Correct. A voltmeter just
So-
tells you stuff.
Okay, so
It
in that
doesn't
case,
change it.
once again, here to here, 0, there's
Yeah.
nothing between. But here to here, with an open switch, would still be 0.
Well, with an open switch, you got the 12.
Oh, because you're,
Yeah, because my pressure, think of it like a water line. If you had 3,000 foot of hose,
I have no idea.
but we're not flowing any water, is the pressure still gonna get through the hose?
Corbin knows.
Well, why not?
oh,
When-
wait,
when-
you said 3,000?
So, say I got 3,000 feet of hose strung out, but the valve is shut. Would I have water pressure at the end of my hose?
Yeah.
I would, because, well, the pressure has all day to get the pressure
Yeah.
there, right? So as soon as if it was water, you'd say close the valve, but as soon as I have flow, now if I have 3,000 foot of hose, a lot of resistance, now I'm gonna have a resistance to that pressure because I have water flow. So that's the same thing we're doing,
Okay.
is if we're not flowing anything, the pressure, the voltage pressure, it makes it through that resistance without any problem, because it takes a little bit,
Yeah.
but a little bit of electricity is not very long. So on a DC circuit, it's like, yeah, no problem, we'll get there. So the full pressure that's coming off our battery is able to get there because we don't have any current flowing.
Okay.
Once we have current flowing, now whatever resistance these guys are, you're gonna end up with a voltage drop on them.
Okay. All right. Thank you.
Oh, we'll review it again.
Yeah.
I think you could help me with the troubleshooting.
The board thing?
Yeah.
Sure thing. Yeah, one quick meeting I gotta do. Okay, I'm gonna grab my sheet. Give me about 10, what is it right now? I'll meet you at quarter after. Parker's on my list. Harrison, wanna catch up in the office here in about 4 minutes? Sounds good. Give me a couple, I'm just gonna get my stuff up in here. So, 4 minutes or so. Yep, when they're done, they go in my mailbox.
my
Now I
goodness.
allow the amperage to flow
Even
through.
better.
Now it takes work to flow through.
Dude, look at this.
So I would have a voltage on each one, so it'd be the same thing if I burn
If I
out a
see my
light bulb.
tears, man.
Now I don't have amperage going through because it can't go through
Right.
the wire. So now at this point, if I were to measure my voltage across here, I'd have the voltage drop. So I got all the pressure from this side. And on this side, I have the negative side coming through, and there's no amperage anywhere, right? So there's no amperage here, so I'd have the full 12 volts trying to jump across there. But because there's no amperage, if you were to draw the resistance triangles for the Ohm's law on these, this one's gonna have 0 in the amps for ohms, which means the resistance is gonna go, well, the resistance doesn't change, right? Resistance. So because the resistance didn't change, and we know the amperage is 0, that means, well, it's gonna be 0 volts then. So without current, that's how the voltage changes. So that's gonna be the lab, is they're gonna be having to take light bulbs out, put light bulbs in, break wires.
So is it like that?
So I did it both at zero, so this wire.
Yeah, 'cause you're both on. Yep.
Yep. So I drew.
Yeah, and when you do that, if you have more, just grab me your bean and
Okay.
we'll go through it.
Because like, otherwise, trying to keep track of it all, it's.
Either way. Is there a specific way?
Draw in a voltmeter and ammeter. So,
Like I could just put my voltmeter here, my ammeter there, and then it would be 0 and then whatever.
so if you put a voltmeter here, are we gonna have current through the voltmeter? No. So we wouldn't actually have a complete circuit. So what they're asking is, they want,
Which is why I was asking.
yeah, they're assuming it's a circuit, so that you're reading the amperage and the voltage.
And are they wanting like artificial voltage put in there?
No, they just, basically what they're saying is, if you were to say, put amp meter in here, we're gonna measure the amp through the resistor, and a voltmeter here will measure the voltage across the
It's
resistor.
just to actually get.
Yeah, exactly, that would be the point.
And then, this one, if you do your resistance calculation from the total, you get a different answer than if you do it in your regular.
Oh,
Comes up to like 30, what? Not 33.
E total, 100 volts, 2 amps, 1 amp, so I have 3 amps total. 33.33. Divided by 250. What are the numbers you're saying that are off? So 2 amps,
Well,
1
yeah,
amp.
you add your 20 here, and then you use the overall resistance to get, it comes out to 30 point, instead of 33.3.
So this would be 100.
But 1 over 100 will work. Or I'm sorry, 100, yeah. Down to 30.
I'll, guessing it's a calculator digit thing, but let me double check that. So we're three ohms off, is what you're saying. The interesting part is that with what they give you, I don't know how we get there other than possibly that 0.7 ohms or something. I'll do that, thank you.
You drop something.
I dropped something, okay, this goes to the other side. Ooh. Oh, dropped something off that, something important. Get a bunch of little, what do they call those, twisted ties? Twisted ties for those rubber bands. All right, ready, Harrison?